once you understand that position or the instant when the spring has maximum length or the spring has maximum elongation, let it be x, and this is the maximum length of the spring. At that instant we have analyzed that both the blocks will move with same velocity. Let that velocities be v. v1 is equal to v2 is equal to v. Previously we analyzed that the energy, mechanical energy of the system will remain conserved. Conservation of energy holds good, because spring force is a conservative force. No friction is there. Friction is a non-conservative force. Therefore, the system is conservative and we can easily conserve the mechanical energy of the system. Secondly, on the system, no net force is applied. On the block 1, the spring force is acting towards left. On the block 2, the spring force is acting towards right. These two forces are equal and opposite forces. Therefore, the net force acting on the system will be equal to 0. They are the internal forces. I told you that the net internal force acting on the system must be 0, and in the system we cannot see any force acting from outside as a whole. Therefore, we can conserve the linear momentum of the system. These two principles will hold good. This is the initial condition. This is the final condition. Initially, the momentum is m2 into 0 plus m1 into v naught I cap. Finally, the momentum is m2 into v I cap plus m1 into v I cap. This gives us v is equal to m1 v naught by m1 plus m2. This equation we are getting by conserving the momentum of the system. These two momenta are equal. This is the conservation of momentum. Next, we can apply the energy conservation principle. The initial energy E1, you can write 1 or you can write I, it's your choice, or you can just write P1 or you can write P2. 2 stands for final, 1 stands for initial, or F stands for final and I stands for initial. E1 is equal to E2. In the system, the total mechanical energy is purely kinetic because there is no potential energy stored in the spring. So U1 is equal to kinetic energy of the system. This block has no velocity, no kinetic energy initially. Therefore, the total kinetic energy of the system will be equal to kinetic energy of this block only. That's equal to m1 into v1 naught square. And spring potential energy is 0. Finally, at this position, when both the blocks will move with some velocity, the spring will have maximum elongation. We can have the kinetic energy of both the blocks, also the potential energy of the spring. Just we have to calculate and add them up. Potential energy of the spring is half kx square, when x is the elongation of the spring, plus kinetic energy of the block 1, that is m1 v square, kinetic energy of the block 2, that is half m2 into v square. This gives us m1 v naught square is equal to kx square plus m1 plus m2 into v square. This equation we are getting by conserving the energy of the system. Now we have two equations and two unknown quantities. We have two equations and two unknown quantities. What are these unknown quantities? One, we have assume x as the elongation of the spring, and second is the velocity of the bodies at that instant, x and v. Just you have to solve. Substitute the value of v from first equation in second equation and you can get the result. When you substitute the value of v from first equation in the second equation, we can write m1 v naught square is equal to kx square plus m1 plus m2, b will be equal to m1 v naught by m1 plus m2 square of this. This gives us kx square equal to m1 v naught square minus this factor can be simplified by eliminating m1 m2 in numerator and in denominator. So we are getting m1 square v naught square by m1 plus m2 whole square. You can take common m1 v naught square 1 minus m1 by m1 plus m2 into this factor, of course, that gives us kx square is equal to m1 plus m2 minus m1, that is m2. So we are getting m1 m2 by m1 plus m2 into v naught square. The elongation of the spring is equal to m1 m2 by m1 plus m2 by k square root of this into square root of the velocity v naught square, will get v naught. The previous problem can be modified in this way. We take two blocks m1 and m2. You project m1 with velocity say v naught towards right and project m2 with velocity 2 v naught towards left. For the sake of simplicity, you can take its mass m and its mass suppose 4m. With a modified question, and the spring is relaxed. How to calculate the maximum elongation of the spring? Find the maximum elongation of the spring. Let it be x. Our theory says that for the understood and explained in the last problem, that the elongation of the spring will be maximum only when both the blocks will move with same velocities. Both the blocks M and 4M let move towards the right with velocity v. At that time, the elongation of the spring is maximum, let it be x. The length of the spring we will not initially, so the final length at this instant, when both blocks will move with some velocity, elongation is maximum, therefore the length becomes maximum. And that is equal to L naught plus x max. X max you can say x. Conservation of momentum holds good. Therefore you can just write Pi equal to Pf or P2 equal to P1. P2 equal to how much? 4mv I cap plus mv I cap. Total momentum of the system, the final position. Total momentum of the system in initial position. In initial position, the total momentum of the system can be found by taking their individual momenta and add them up. Momentum of this particle is 4m into v naught I cap. Of this particle momentum, it is moving backward, therefore its momentum is equal to m into minus 2 v naught I cap. So we can just write 5 into m into v will be equal to 4 m v naught minus 2 m v naught, will get it as 2 m into v naught. This gives us v equal to 2 by 5 v naught, equation number 1. The next principle is conservation of energy between these two positions. Here the total energy is E1. Here the total energy is E2. Here E1 is equal to kinetic energy plus potential energy. Here the total energy is equal to its kinetic energy plus its potential energy. Kinetic energy of the initial system is equal to kinetic energy of this block half into its mass into its velocity square plus kinetic energy of this block, which is equal to half into its mass into the square of its velocity. Since the spring is relaxed, no potential energy. Here kinetic energy will be half 4m into v square plus half m into v square plus additional energy, that is the potential energy of the spring, comes because the spring is elongated. That's half kx square. Here you are getting 2m v naught square. Here we are getting 2m v naught square. So in left hand side you are getting 4m v naught square. Right hand side you are getting 2m v square plus half m v square, that is 5 by 2 m v square plus half kx square. This is the equation we are getting from energy conservation. Substituting the velocity v from equation 1 and equation 2, we are getting 4m v naught square is equal to 5 by 2m. V is equal to 2 by 5 v naught square of this plus half kx square. That gives 4m v naught square, 5 by 2 into m, 4 by 25 v naught square plus half kx square. Two getting cancelled, 5 will get cancelled, 25 to get 5 in the numerator. So 4m v naught square is equal to 2 by 5 m v naught square plus half kx square. You bring this factor to left hand side, it becomes minus 2 by 5 m v naught square is equal to half kx square. 5 into 4 20 minus 2 18 m v naught square by 5 is equal to half kx square. In the final step you are getting x is equal to 36 m v naught square by k square root of this. 5 will be there in the numerator. So 36 square root is 6, v naught square root is v naught m by 5k square root of this answer. So the basic idea behind this problem is to calculate the initial momentum. Vectorially you should be very careful. Find the final momentum, keeping this fact in front that both the blocks will move with same velocities. To calculate the maximum elongation of the spring, after finding the final momentum, equate it to the initial momentum to get the velocity at this instant. And the second equation is the energy conservation equation. Initially you had the energy and finally what will be the energy. Finally we have the potential energy in addition to kinetic energy. Initially we have kinetic energy but no potential energy if the spring is relaxed. But in some problems they may compress or elongate the spring and at the same time they will give some velocities to these blocks. In that case you can take the elongation or compression or deformation of the spring into account and you can write that potential energy factor in the initial energy and equate it to final energy. So in this way we can solve the problems of two particle system connected by a spring when they are constrained to move along a smooth horizontal surface. Let us discuss this problem, which is a system of a block of mass m1 and this wedge of mass m2. This is a particle, this is also a particle. So this is again a system of two particles. The block is projected towards right with a velocity v naught on the horizontal plane. And this is a wedge. The block will go and climb onto the wedge. While doing so, the velocity of the block will change, its direction will change, its magnitude also will change. Therefore, the block M1 will experience a force from this wedge. In which direction? That we can calculate. And in return, this block will provide a force to the wedge which is equal in magnitude and oppositely directed. So long as the block will be in contact with the wedge, they push each other along the normal direction to the slant. This is the normal direction. This is the force offered by the wedge on the block, and this is the force offered by the block on the wedge. They are action reaction pair. If you call it action, this will be reaction. If you call it action, this will be reaction. They are action reaction pair. They are equal and opposite and acting along the same line. But for the exaggerated of clarity, this is exaggerated for the sake of clarity here, showing that these two forces are not acting along the same line. For the sake of simplicity, I have drawn the diagram. Exactly, it should be like this. But if I draw like this, we cannot distinguish whether this force is acting on the block 1 or this force is acting on the wedge. Or if you want to write this diagram, just make a little separation between the block and the wedge, and it becomes very clear now. This force is acting on the wedge, this force is acting on the block. These two forces are equal, opposite and collinear. And ground exerts a force. Let it be NS, normal reaction force, in vertical direction. Apart from this, gravity pulls both the bodies down. With the forces equal to their weights, M1G and M2G respectively. Since there is no friction, we have assumed the friction force will be absent in our free body diagram. Since the frictional forces are absent, there is a possibility of conservation of mechanical energy. Since friction is absent, non-conservative force is equal to 0. Therefore, work done by the non-conservative force is equal to 0. And these normal reactions are the constant forces, and in last classes I proved that work done by constant forces as a whole will be equal to 0. Work done by the non-conservative force will be 0 when you call the friction non-conservative, and work done by this normal reaction forces N1, N2 and Ns as a whole will be equal to 0 for the system, for this is the system. Therefore, applying work energy theorem, we can write work done by conservative force plus work done by non-conservative force, that the total work done on the system is equal to change in kinetic energy of the system. Since non-conservative forces will do no work because these non-conservative forces are absent, and the constant forces, even though they are not conservative, when you consider this block 1 or the wedge 2 separately, but as a whole they will do 0 work. Hence you can write work done by the conservative force is equal to change in kinetic energy. These conservative forces, that is gravity, they continue to act and they do work. Gravity does work at the expense of its potential energy. So you can just write work done by the conservative force is equal to negative of or loss of its potential energy is equal to del K. So you can prove that del U plus del K will be equal to 0, or total energy of the system, mechanical energy of the system remains conserved. So we can write by analyzing the system that energy conservation must hold good. So the first condition, energy of the system initially must be equal to energy of the system finally. Kinetic energy plus potential energy initial must be equal to kinetic energy plus potential energy final, or you can just write change in kinetic energy plus change in potential energy of the system must be equal to 0. Next, observing the free body diagram, these two forces are the internal forces. As a whole, they will be equal to 0 when we add them. And this normal reaction, even though this is acting from outside, and these two gravitational forces acting from outside by the earth have no component along the horizontal direction, because these three forces are acting vertically. This is acting vertically up, these two forces are acting vertically down. They cannot have any component along horizontal direction. Hence you can write that along x direction or horizontal direction, no net force is acting on the system. Therefore, the horizontal momentum of the system will remain conserved. But you cannot conserve the vertical momentum of the system, because net vertical force, that is Fy, is equal to n dash minus m1g minus m2g j cap may not be equal to 0 or is not equal to 0. Therefore, vertical momentum cannot remain conserved. That's very interesting. You can conserve the linear momentum of the system, but not in vertical direction. In which direction you can conserve? In horizontal direction you can conserve, but not in vertical direction, because vertical force is not equal to 0. The net vertical force is equal to this much. And thus, in j cap direction, m1j in minus j cap direction, m2j in minus j cap direction. In other words, we can say that acceleration of the center of mass along horizontal direction will be 0. However, acceleration of the center of mass along vertical direction may not be equal to 0. So this is the analysis. We can conserve the mechanical energy, so also the linear momentum. In which direction? In x direction or horizontal direction only. After this, we can proceed by writing the two sets of equations and we can solve. After analyzing the situation and understanding the fact that this system will definitely obey the principle of conservation of mechanical energy, but along one particular direction only, that is the horizontal direction, we can conserve the linear momentum. Now let us proceed to solve the problem by writing two sets of equations. Let us assume that the wedge which moves towards right by experiencing a net horizontal force by the block M1. This normal reaction is offered by the block M1. Block M1 is in contact with the wedge. Therefore, it is pressing the wedge in this direction, and the wedge is being pushed by the ground in upward direction. This normal reaction has horizontal component, so also the vertical component. This is Nx, this is Ny. In addition to all, gravity pulls the wedge towards down. If you look at the wedge along the vertical direction, the wedge cannot accelerate because this ground is rigid and not accelerating at all. Therefore, acceleration of the wedge along vertical direction will be equal to 0. Now come to the block 1 having mass M1. Block 1 is being pushed by the wedge in opposite direction with a force of equal magnitude, and gravity pulls the block down. We cannot expect that net force acting on the block along vertical direction will be equal to 0. Acceleration of the wedge along y direction will be equal to 0, but acceleration of the block, this is the block, this is the wedge, along y direction is not equal to 0. Why? When it is moving with respect to the ground, up and up, its y coordinates will increase. Therefore, we can speculate that the second derivative of the y coordinates with respect to time may not be equal to 0. If this is understood using the basics, we can write that the net force acting on the block in vertical direction, that is n cos theta minus mg is not equal to 0. Some students they just write n cos theta is equal to mg. Some students they write n is equal to mg cos theta. Without understanding or analyzing the system physically, they write these two equations. Neither this equation n cos theta is equal to mg, nor this equation n is equal to mg cos theta may be correct for all the cases. So you should be careful. I am analyzing the particles of the system one by one along horizontal direction, along vertical direction. Along vertical direction, its acceleration is not equal to 0. whereas the acceleration of the wedge is 0. Therefore, acceleration of the center of mass along vertical direction is equal to m1a1 y plus m2 a2y by m1 plus m2. When a2y will be equal to 0, a1y is not equal to 0, we should expect that the center of mass must accelerate along vertical direction. Whether it will accelerate down or up, that is the next question. However, along the horizontal direction, no net force is acting. Therefore, the center of mass acceleration along x direction will be equal to 0. Or you can say velocity of center of mass along x direction will remain constant. Or we can say momentum of the system along x direction will remain constant. To get the maximum height, this block will go on climbing onto the wedge at a particular position, say this position. It will not move with respect to the wedge. The relative velocity of these two bodies will be exactly equal to 0 at that instant. If it is not 0, if the block 1 keeps on sliding with respect to the wedge m2, then this height will go on increasing. When the height will be maximum, the block must have to stop relative to the wedge instantaneously, then it comes down with respect to the wedge or slides down with respect to the wedge. Hence, at the maximum height, both m1 and m2, the block and the wedge, must have same velocity, just like the last problem. At the time of maximum elongation, both the blocks must move with same velocity. Similar type of logic. When the height becomes maximum, this will stop sliding with respect to the wedge. Then both the bodies will move with some velocity instantaneously at that position. Let us assume that their velocities v let. Then we can apply these two conservation principles. Principle number 1, momentum conservation. Initial momentum will be equal to final momentum. This is the initial condition. This is the final condition. Initially, for the sake of simplicity, the wedge is not moving and the block is moving. Therefore, the initial momentum will be equal to momentum of the block only. In positive direction, I am not writing plus k cap. Instead of that, I am writing just plus. Finally, at this moment, both block and the wedge will move with same velocity towards the right. Therefore, their momenta will be m1v plus m2v. This gives us the velocity of both the bodies at that instant, which is equal to m1 v0 by m1 plus m2. Equation number 1. Well, next, come to conserve the energy. Kinetic energy plus potential energy change as a whole will be equal to 0. Final kinetic energy will be equal to half m1 v square plus half m2 v square. Initial kinetic energy is just half m1 v0 square. This is the change in kinetic energy. Change is always final minus initial. So this is the change in kinetic energy. Change in potential energy. This block is moving up. This wedge is moving towards the right. The center of mass of the wedge does not change its height. Therefore, the gravitational potential energy of the wedge does not change. Since the block is moving up and up, the gravitational potential energy of the block will increase from 0. If you take this ground level as the reference level to the maximum value m1gh. This is the change in potential energy of the system is equal to change in gravitational potential energy of the block, because the block only is increasing its energy, changing its energy from 0 to m1gh. So del u will be equal to plus m1gh will be equal to 0. This is the equation number 2. We can simplify this. Half m1 plus m2 into v square minus half m1 v0 square plus m1gh will be equal to 0. Now we have two equations and two unknown quantities, v and h. Now you substitute v from equation 1 in equation 2 to obtain half m1 plus m2 into v, that's equal to m1 v0 by m1 plus m2, square of this, minus half m1 v0 square, that's equal to minus m1gh. We can take common some factor m1 v0 square by 2, m1 v0 square by 2 minus, we will get 1 minus m1 by m1 plus m2, and that's equal to minus m1gh. If you simplify the term, m1 plus m2 minus m1, that will be equal to m2, m2 into m1, that is m1 m2, by m1 plus m2 by 2 into v0 square, negative of this is equal to minus m1gh. And next step, you are getting your answer of the maximum height, that's equal to h, will be equal to m2 v0 square by 2 m1 plus m2 into g. or you can just write v square upon 2g into 1 plus m1 plus m2 answer.